Okay, YouTube, in this video we're going to continue to explore solving trig equations, but specifically trig equations involving what we refer to as multiple angles. And multiple angles, essentially, they're pretty easy to recognize because they are multiples of the variable that are contained in the angle here. So we say a half times x, which is what really x over 2 is, or 3 times x, what we do to solve for these angles here. And so notice that our instructions do ask us for all solutions on the interval from 0 to 360 degrees. And so we're working in degrees and we only want a restricted amount of solutions. So let's go ahead and take a look at how I would solve this here. First things first, I would just isolate the trig function. And so this is really kind of the same method that we've been using here, isolating the trig function. The very first step I would take to do so is go ahead and divide both sides by 2. So we have the sine of our angle here, and our angle just happens to be a 3x. This is equal to a half. The interesting thing is that now that we've isolated our sine function here, we're going to look at what kind of a reference angle would have caused our sine function to be equal to a half in the first place. So with respect to reference angles, and just looking at 30, 45, and 60 here, we could look at any of the other quadrantal angles on the unit circle, but we didn't get anything equal to a 1 here or a 0 here or anything undefined like that. So we're going to look at these angles for which we know our values really well. So we say sine would come out to be a half if and only if you were talking about some sort of pi sixth or 30-degree reference angle. So what we're going to do here is this. We're going to say, well, then our angle here, 3x, that would have to be equal to 30-degree reference angle, stops. Okay. So because we would say that sine came out to be positive, what quadrants would we have to be in? We would have to be in the first or the second quadrant here. And because these are 30 degrees here and here, we could essentially dig out our angles in standard position. So we'd say 3x, that would have to be equal to 30 degrees. Okay? And what I'm going to write here is plus 360 degrees n. And also 3x would have to be equal to this angle here, 150 degrees. Okay? Plus multiples of the period of sine. Now, interestingly, once we get to this point, we still haven't gotten x by itself. So what our job is basically to divide both sides here by whatever the coefficient of your angle is. And so our single angles then become this. We'd say a third of 30, which is 10 degrees, plus a third of 360 is 120 degrees n. And I'm going to put a box around this. We're also going to list here that x is equal to a third of 150, which is 50, plus a third of 360 n, which is 120 degrees n. And so these solutions right here are all infinitely many solutions, but what we were asked to do was list all solutions on the interval from 0 to 360 degrees. So what we're going to do is essentially this. We're going to substitute integers for n until solutions fall outside of the desired range, outside of the desired range. And so essentially, because we want answers between 0 and 360, when I look in, say this first answer here, we say x is equal to 10 plus 120 degrees times n. If we say let n be equal to 0, then what we get is this. We get x is equal to 10 degrees plus 120 degrees times 0. Or in other words, we get x is 10 degrees. But what I want you to notice is if you plug in n equals 1 into that first one there, then what we get is x equals 10 degrees plus 120 degrees times 1, which is really 130 degrees, which still falls in that interval. So far we've grabbed this here. What if I plug in n equals 2 into this first solution equation here? Then I would get x equals 10 degrees plus 120 degrees times 2. And we would get this is x equals 200, and this would be 40 plus 10, 250 degrees. And if we were to add on now, say another n here, we say n equals 3. n equals 3. We would get x, pardon me here, our answer was 10 degrees plus 120 degrees times 3. What I want everybody to see is that this one wouldn't be included because we get 360 degrees basically plus 10, which is equal to 370 degrees. And so this basically, even though it would be a solution to this, we would say we would not include it because 370 degrees falls outside of our range of solutions. So what we've got so far is 10 degrees, we've got 130 degrees, and we've got 250 degrees. Now what we're going to do is go back and we're going to plug in n equals 0, 1, and 2 into our second equation here. So we would get this. We would get x equals 50 degrees plus 120 degrees times 0. We get x equals 50 degrees plus 120 degrees times 1. We may be able to get away with this, 50 degrees plus 120 degrees times 2. And I noticed that last time when I made it up to 3, we went outside this range. So I suspect the same thing is going to happen here. So our x values happen to be these here. We would say 50 degrees. Looks like 50 plus 120 is 170 degrees, and 50 plus 240 there would be 290 degrees. So I'm going to list these up here as well. We would say 50 degrees, also 170 degrees, and 290 degrees. And so when it comes to multiple angles, what happens is we still solve these normally, but what we do is end up having to find all solutions between, say, 0 and 360 a lot of the time by plugging in values for this n here until we, say, fall outside that region. So taking a look at example B here, let me try to quarantine this off. It's a whole lot of writing. Basically, if we look at this and we say cosine of x halves equal to root 2 over 2, I already noticed that the trig function is by itself. So we say, okay, well then what is this angle x halves equal to? And so noticing that this is root 2 over 2, first of all, root 2 over 2 would only happen if cosine had a 45-degree reference angle, or it was a 45-degree reference angle if cosine came out to be root 2 over 2. And I noticed that we have a positive cosine value here. Root 2 over 2 is positive. So in terms of quadrants, we either had to be in the first quadrant or we had to be down in the fourth quadrant. And we know that each of these has a 45-degree reference angle. And so our two angles here, looks to me, are 45 degrees, but also x halves would have to be equal to 45 degrees short of 360, which comes out to be 315. So now, just like we did on our last one here, we're going to say plus multiples of the period of the function. And because 2 pi, or 360 degrees is the period of sine and cosine, we're going to write plus 360 degrees in. So now the last thing we basically need to carry out in this particular case is we need to take both sides of this equation times 2. So if we were to take this left side times 2 and the right side times 2, what we end up with instead is this. We get x is equal to 2 times 45 degrees, which is 90 degrees, plus 2 times 360 degrees, which is 720 degrees, n. And then from here, when we take both of these sides times 2, what we end up with is x is equal to 2 times 315, which is 630 degrees, plus 720 degrees, n. So in terms of plugging in values of n here, I'd say, maybe start by plugging in 0 for n. And with just this first one here, you'd see that you get 90 degrees plus 720 times 0. This would be one solution value. But if you plugged in even 1 for n here, you get 810 degrees, which doesn't fall in this range of outputs. And likewise down here, if you plug in 0 for n here, we get 630 degrees, which already doesn't fall within this range. So the only solution that this equation has on the interval from 0 to 360 is the 90-degree solution. Cheers.